Hello and welcome everyone to INE's webinar for path selection in EIGRP. I believe you guys should be able to hear me and see me. For some of you who do not know me, my name is Rohit. I'm a full-time instructor with INE. I have 5 CCIEs, CCIE in route switch, security, voice, collaboration, and service provider. I do have intentions to do one more, which is going to be DC in the new blueprint once we get out of home. So without wasting much time, let's get started with path selection. So what we're going to be doing is, because it's a limited time for the webinar, we would be using this diagram to demonstrate configuration and path selection, how EIGRP does path selection. So now the first thing that I want to talk about, just quick talk about, is how does EIGRP form neighborship? What are the prerequisites for EIGRP to establish adjacency? So the first thing would be autonomous system has to be the same, and the K values must match. The IP address or the subnet on which they're connected, they should be in the same subnet. I think that's about it that you require for EIGRP to establish neighborship: K values and AS number. So once they establish the adjacency, they would start exchanging routes. And EIGRP has internal routes, which is the administrative distance would be 90. I have external routes where the 80 would be 170. And then we have the null zero summary prefix, which is null zero route, which is 5. So as of right now, what I've done actually, what I've pre-configured, let me in fact take this here. So what I've done is I've pre-configured EIGRP on all my routers, R1 through R10, and all of the routers are running EIGRP AS100, and they all are running classic EIGRP. There are 2 different types of implementation for EIGRP. We have classic versus named. Classic is 32-bit and named is 64-bit. So let me just quickly show you that. If you look at my configs, show run section router EIGRP, I have classic EIGRP implemented here for router 1. And I have changed my K values just for a task, which I would be showing you. I have basically eliminated bandwidth from the K values. So bandwidth would not be considered for metrics. Only delay would be considered for metrics. Again, this is only from perspective of simplicity because of time constraint. And I have one more router here, which is router 8, which has been pre-configured as named EIGRP. So configuration is pretty much similar to classic EIGRP. The only difference is that named EIGRP is address family based. So we have IPv4, IPv6, we have VRFs. Everything can come inside one EIGRP instance rather than you having a separate one for IPv4, separate for IPv6, and separate for VRFs. So I have configured all of the routers running classic. Only 2 routers, router 8 and router 10, they are basically running named EIGRP. Like I said, named EIGRP is 64-bit, and the K values are K1 through K6. And named EIGRP is backward compatible with classic as long as you keep K6 turned off, which if I go back and do a show protocols, or in fact, let's do a show IP protocols, you would see that it is 64-bit and I have 6 K values, K1 through K6. Because K6 is 0, it becomes backward compatible with classic, so it's not going to be a problem. But if you were using K6, which is for energy and jitter, if you were using that, or let's say you were running named EIGRP and you were running classic, then you have to turn K6 always off. So as of right now, EIGRP completely configured. All the routers have routes to each other. They are loopbacks. They all are reachable. Let me in fact quickly show you that. If I do a show IP route EIGRP, you would see that I have all the routes in my routing table. These are the loopbacks of all the routers. So 150.1.1.1 is the loopback for router 1, and router 2 is 151.2.2, 151.3.3, and so on. So as of right now, I have all the routes. So let's purely focus on path selection, how EIGRP is going to do path selection, and how does it select the best path and maybe a backup path like a feasible successor, and maybe load balance. We look at all those things right now. So the first thing what I want to do is talk from the perspective of router 6. If you look at router 6 right now, router 6 has multiple paths to reach the loopback of router 9. It could go directly through R7 and reach router 9's loopback, or it could transit from R1, go through R3, go to R7, and then go back to R9. So it does have multiple paths, which is available to him, but which one is he going to choose? That depends on the metrics, right? Since I am not using bandwidth for metrics, default EIGRP uses bandwidth plus delay. If you look at the metric calculation, metric is equal to bandwidth plus delay, where bandwidth is equal to 10 to the power of 7 divided by the lowest bandwidth. And delay is total delay divided by 10. You add both of them, bandwidth plus delay, times the constant, which is 256, that becomes your metric. For example, let's say we will look at any one router. Let's just pick one router. Maybe we'll pick, let's say, router 5, and we'll look at what's the metric to reach router 9's loopback. What's the metric? Let's look at that. So if I look at my routing table of R5 and do a show IP route 150.199, what metric do I see here? I see 129.024. Now, how do I get that? How does the metric get calculated? So obviously the lowest cost or the lowest metric, that's what's going to go in the routing table. EIGRP does load balancing if it's equal cost path. It will also do load balancing if it's unequal cost path, depending on if you make it qualify as a feasible successor, and then you have variance also. As of right now, I'm not really talking about that. I'm just talking about how metrics gets populated in the routing table. So if I look at this metric, typically it is what? If I look at the metric, so metric equals bandwidth plus delay times the constant. Constant is fixed, which is 256. And bandwidth equals 10 to the power of 7 divided by lowest bandwidth. And delay would be total delay. So total delay divide by 10. Add whatever value you get. Let's say you get a value of X here. You get a value of Y here. Add X plus Y times 256, that becomes your metric. So as of right now, I'm using only delay for my metrics, right? So if I look back at my routing table, I see that the total delay is 5040. That's my total delay. So if I look at the formula, since I'm not using bandwidth, this would be 5040 divided by 10. So that becomes 504 times the constant. So 504, let's pull up a calculator. All right, so I have a calculator here. So 504 times 256, that becomes 129.024. That's my metric. That's how EIGRP calculates the metric. But named EIGRP it's slightly different from metric perspective. The formula is different. So if I look at, let's say, R8 to reach let's say to reach 150 9.9, to reach this network, I see a metric of 2585600. Now, how does this come in? What's the delay that I see here? The delay I see is 5050. If I use the same formula, which I did for classic EIGRP, you would not get this value because R8 is running named EIGRP. So the formula is different for named EIGRP. This is only for classic. This is only for classic. So if you want named EIGRP, named it's pretty similar, but the constant is different. So metric equals bandwidth plus delay times the constant, where the constant is not 256. The constant is 65536. So that's the constant. And bandwidth is still the same, 10 to the power of 7 divided by lowest bandwidth. Since we are not using bandwidth, we're only using delay. Delay would be total delay. Do not divide this by 10 because delay in named EIGRP is in picoseconds. It's not in microseconds or tens of microseconds. In classic EIGRP, it is in tens of microseconds, but in named EIGRP, it is in picoseconds. So I keep the value as it is, which means since I was seeing a metric or delay of 5050, I would keep that the same. So 5050 times this constant value. Let's try and do that. So if I use my calculator again, I have 5050 times 65536 equals, I get this value. That's my metric. That is my metric. But what do I see in my routing table? I see 2585600. It's not the same. The reason you don't see it the same is because the routing table is 32-bit and named EIGRP is 64-bit. So what EIGRP does, it converts 64-bit metric to 32-bit metric and puts that in the routing table. In fact, if I look at the EIGRP topology table, you would see this metric. Let's in fact have a look at that. Show IP EIGRP topology 150.199, 255, 255, 255, 255. And I see a metric of 330956800. That's my metric for named EIGRP. And if you look at the rib, what does it send in the rib? It sends 2585600, which we saw here. Now, how does he get that? That's a 32-bit metric. See, both the metrics are pretty much the same. One is a 64-bit metric and one is a 32-bit metric. So EIGRP converts it to 32-bit metric and sends that to the routing table because the routing table is 32-bit. So how does he get that value? So if I do a show IP protocol, you would see there's something here called as the rib scale, which is by default 128. The rib scale is something that you can adjust, but the constant cannot be adjusted. Default rib scale is 128. So to convert from a 64-bit metric to a 32-bit metric to send it into the rib, I have to further divide this value with the rib scale, which is 128, and I get my metric, which is in my routing table. So if the metrics are same, EIGRP is going to load balance. If the metrics are not the same, only the best path goes in the routing table. Now, how many paths EIGRP would do load balancing for? Let's say if it had equal path, how many paths would it do? Default is 4. So if I have 4 equal cost path, it would do a load balance, but you can change that value. I believe it goes to 32 also. So you can have like a maximum path of 32. So this is from metric perspective. So looking back at our diagram, if I look at R6, let's say if R6 needs to get to the loopback of R9, which is 150.1.9.9. And as of right now, without even me looking at the routing table, because all the interfaces are gig ports, and I'm not using bandwidth, and my delay, I haven't changed anything on any of my interfaces, so delay would be the default delay for the gig port. I believe the delay on this link is 1. I believe the delay on this link is 1, and the delay on the loopback is 500. Delay on this link is 1. Delay on this link is 1, and delay on this link is 1. So now from R6's perspective, he has 2 paths to reach R9's loopback. The first path has a total delay of 502. So lower the delay, better is the metric, or lower would be the metric. Lower is better. So because my delay from R7 is lower, obviously that would be the best path. So if I look at the routing table of R6, he would choose R7 to reach 150.199 because that's the best path, is the shortest path to get to that destination, lowest metric, right? Now, what if I say that I need you to ensure that R6 transits R1 to reach that loopback? What are the different ways that I can achieve that? So let's think about that. So one way to achieve that is, in fact, a lot of people say that let's increase the delay or the bandwidth on the interface. So maybe I go to this interface here and I increase my delay on this link. I maybe make it 100. I increase my delay. Yes, that could be a solution. But think about from a lab exam or even production perspective. Let's say your boss tells you, hey, we need that you should ensure that this router transits maybe router 1 for some reason, or maybe in the lab exam, they ask you that R6 should transit R1 to reach 150.199. If I go and do something like this, that I change the bandwidth or change the delay on the interface, it affects all traffic, all networks. Because me changing the interface bandwidth or interface delay, I really can't specify for which network. So that would not be the right way of doing it. Yes, you achieve your requirement, but it's like saying, I'm asking you to permit a certain guy to access a certain network, and you just do an access list permit IP any. Does that make sense? Yes, it works. It works for him, but it works for everyone else. So that would not be the right way of doing it. So changing interface bandwidth, changing interface delay, not the right way to do it. Let's say another way to achieve this could be maybe I put a static route on R6. I put a static route which says, okay, to reach 150.199, next hop is router 1. Yes, that could be a solution, right? But can you do that in the lab? No, because static routes are not permitted in the lab exam unless explicitly told. So again, static route would be something that you cannot do. Third way of achieving this could be maybe I do like a policy-based routing where I do a PBR and say, okay, R6 will transit next hop router 1. PBR could be a solution, but PBR again is not permitted in the lab exam unless explicitly told. So you really have to think from an EIGRP solution perspective. Because we're actually running EIGRP, so you have to think from EIGRP's perspective. So how can I change EIGRP or do something in EIGRP so that my path for R6 to reach 150.199, it goes through router 1. The correct way to achieve this would be I could change the metrics. The metric can be changed with a feature called as offset list. Offset list is used to tell the router to take a certain path because we're actually changing the metrics. So offset list is purely used to change the metrics. So maybe we'll try that. Let's try and do that. There are many more ways of actually doing that. We'll discuss that. But right now, let's assume that offset list is the best way to do path manipulation and ensure that R6 transits router 1 to reach 151.99, and it does not affect any other routes. We don't want any other routes to be affected, so only 151.99. So to achieve that, what I could do, now offset list is something that you can do outbound or you could do inbound. It's always done in the direction of control plane. So if I was doing outbound, I would have to configure R7 because R7 is giving the route to R6. So when R7 gives the routes to R6, the 151.99, I will tell R7, increase the metric. Don't rely on the default delay. Add maybe some metrics to it. Increase the metric. So I could do this outbound, or I could do this inbound on R6. So when I receive the route from R7, I will increase the metric. So it's really up to you how you want to do it, outbound or inbound. It depends on the router again. So if the question in the lab exam says configure R6, then you would say inbound, offset list. If the question says achieve this, but do not touch R6, in that case, I would do outbound on R7. I'm allowed to touch R7, not R6. So it all depends on the question. Let's assume that we have to configure R6. So what I will do is I will first create an access list. Let's say an access list 1, permit, and match the route. So 151.99. Now, when you match in the access list, it must be an exact match as per the routing table. If your route in the routing table is a /24, your access list must match /24. If your route is /32, it must match /32. My route is a /32. That's why I'm giving as permit 151.99. And I don't need to give the submit mask or wildcard mask. So I have an access list 1, which matches that specific prefix. Next thing, I go to router EIGRP 100, and I use the command offset list, and I call for the access list 1, and then I have the option of inbound or outbound. Am I receiving the update or am I sending the update? Since I am configuring R6, I would say when I receive incoming, so when I receive update as per access list 1, so when I receive 151.99, increase your metric. So let's say I increase the metric with, let's say 513. I increase my metric. If I actually give 512, my metric would be equal, because right now through R7 is a better path, and through R1 it has 512 metric extra or higher. So if I actually give 512, both the paths become equal, and it becomes equal cost path load balancing. EIGRP does load balancing automatically. Let's in fact see that. So offset list 1, when I receive the update, add a metric of 512 when you receive the update from gig 1.67, which is the link that connects to the neighbor R7. So when I receive from R7 inbound 151.99, I would add a metric of 512. What's the effect going to be? If I look at my routing table now, show IP route 151.99. Let's do a show IP route 151.99. I see 2 paths. And if I look at the share count is 1:1, which means it's doing a load balancing, because the metrics, if you look at the metrics, it's the same, exactly same. I don't want to do that. What do I want? I want that R6 to choose R1. So obviously I'll increase my metric a bit more. Let's go back and remove this. Let's remove this and re-put it back with maybe 513 as the metric. So now through R7 is 129.025 versus through R1 it is 129.024 total metric. So obviously R6 would choose R1 because the paths are not the same, the cost or the metric is not the same, only the best path goes in the routing table. So if I look at my routing table now, I would only see one path through R1. So my traffic now flows through R1 because of shorter path or lower metric. So trace route to 150.199. It is choosing R1, R1 through R3, R3 to R7, R7 to R9. That's how my traffic is flowing. So I did a path manipulation using offset list. Now, let's say I've implemented this and suddenly maybe my boss has changed, or maybe my manager has changed, and he comes back to me and saying, hey, I don't really like this, so I want you to ensure that R6 goes back to R7. I want you to ensure that R6 transits R7 as the best path. Okay, or let's say this was a lab question. Lab questions are normally sometimes they're weird. They ask you something that you would never do in production, but that's okay. So let's say there was a requirement which said, okay, R6 should transit R7 to reach 150.199. Do not change the metrics. So now what do? Even though my metric through R1 is now lower than through R7 because I did offset list. Even though my metric is lower through R1, I must still choose R7. Even though the metric through R7 is higher, I must still choose that. Now think about how I can achieve this. So how can I do this? Metrics, right? I can't change my metrics. I want my metrics to be overridden. So I don't want R6 to use metrics for path selection. I want him to not look at the metric. So think about it. What comes before metric? You remember the path selection in routing table. How does it choose the best path? It's always longest match. Then the second is what? Administrative distance, AD. If that is the same, it then goes to metric. So right now, R6 receives /32 from R7. He receives /32 from R1. So prefix length is same. They both are EIGRP routes. AD value is 90, internal EIGRP. So that's the same. Now it compares metric. Metric through R1, because of offset list, is lower than R7. So he chooses R1. So if I want that, I don't care about metrics, I want R6 to go through R7, I can change the distance. So I can do path manipulation through distance also. However, distance is something that you cannot do outbound. Distance is local to the router. So it's only local to the router. So if I want R6 to choose R7 in spite of higher metric, I can do distance. Let's try this. So I'm going to go back to R6 and go to router EIGRP, if I can spell that right, EIGRP 100, and give the command distance. Now I could change the distance for all EIGRP routes. Like I could say EIGRP and then change the internal distance for all internal EIGRP routes and all external EIGRP routes. I don't want that. I want to change the distance for just one specific route. So I would say distance, let's say 91. I'm increasing the distance. If I receive the update from my neighbor, which neighbor? Let's do a show. Let's do a show IP EIGRP neighbors. So I have R1 as my neighbor. So if I receive an update from this neighbor, 0000, which is my wildcard mask, access list number 1. This is the same access list that I use for offset list. I'm using the same access list. I could create a new access list, but I'm just using the same one. So when I receive access list 1, which means 150.199, when I receive this update from this specific neighbor, I am going to increase the distance to 91. The minute I do this, if I look at my routing table, 150.199, as of right now, I was going through R1, right? My distance was what? It was 90. That was my distance. And if I look at my route now, let's do, if you see right now, my distance is 90. If I do a show IP route 99, 151.99, I'm now going through R7 because the distance is 90 through R7 and the distance through R1 is 91. You can see that if I shut down the interface, let's say if I go back to 67 and shut this down and look back at my routing table, you would see that it is now going through R1 and the distance is 91. So it now prefers R7. Let me do a no shut. So it now prefers R7 because of distance in spite of higher metric, because distance comes before metric in path selection. So distance could be one way of doing a path selection or changing your traffic flow for a specific route. Again, you have to use an access list to match that specific route. Let's say your boss goes crazy again, or maybe the lab exam is pretty weird, or your boss is crazy. He says, okay, let's change this. Don't remove anything. Make R6 go back to R1. In spite of your distance, in spite of your metrics. I don't care about that. I need that R6 should choose R1 as the best path to reach that one specific network. How can I achieve that? Now, I can't change my distance because maybe my boss doesn't want that, maybe the lab restricts that, or I can't change my metrics. So another way to do path selection could be prefix length. You know, prefix length comes before distance, right? If I go to maybe R7, now, if you look at the diagram, if I go to R7, and let's say if I summarize on R7 towards R6 and not towards R3, if I summarize on R7 towards R6 but not towards R3, in that case, R6 would receive maybe a /24 from R7, but a /32 from R1. In that case, it won't even compare distance. Prefix length wins. So let's try and achieve that. Maybe I go to, if I look at right now, trace route to 150.199, I am going through R7 in spite of higher metric because of lower distance. But if I go to R7 now, and maybe I go to my interface gig 1.67, and I say IP summary address EIGRP 100, and I summarize the loopback of R9 from /32 to maybe 150.190/24. Maybe I summarize it. The effect of this would be if I look at R6 now and look at his routing table, show IP route 150.199, he is now choosing R1 because this is a longer match. And if I do a show IP route EIGRP, you would see that he has 150.190, which is /24 coming from R7, but he has a better match, which is a /32 longer match that would be preferred over anything else. So it's always prefix length first. If that is the same, it is going to be your distance. Distance could be between routing protocols, or it could be within the same routing protocol. So if the distance is same, it then goes to metrics. And if the metric is same, it would load balance. If the metric is not the same, then only the best path goes in the routing table. So this was some path selection. We will quickly look at load balancing in EIGRP now. So in fact, there's one more way to do a path selection. Let me in fact talk about that also. There's another way to actually do path selection. But the only problem in that way is that you don't have a backup. So for example, let's say if I tell you that R6 must always transit R7. It must always go to R7. What comes before prefix length? So first was prefix length, right? Then distance, then metric. But what comes before prefix length? The update. If I filter the update, he never gets the route. In that case, R6 would choose R7. So if I want him to go back to R7 now, right now, because of prefix length, if I do a trace route to 150.199, he is going through R1. But if I want him to go back to R7, I could maybe filter the route. If I filter the route, automatically R6 won't have a choice. He would go through R7. And filtering can be done through distribute list. So again, distribute list has two functionalities. It could be used for actually filtering a route, or it could be used also for path selection by filtering the route again. So two ways to look at it. Again, that really depends on how they word the question. If they want a backup, that maybe if this fails, then it should go to R1, then you can never do route filtering or distribute list or filter the route. Actually, technically, we could still do that. We could still maybe use distribute list, filter the route, and then maybe go to R1, do a summary, default summary prefix. We could send a default route to R6. In that case, he has a backup. So just to think about it. But yeah, I mean, if I want him to go to maybe R7 again, I could do filtering. Let's in fact try it out. So maybe I'll create an, now distribute list, you could use an access list, you could use a prefix list, you could use a route map along with distribute list. It's really up to you. Let's try and use maybe a route map. So I'm going to create a route map. Let's say from router 1, I'll say deny. So whatever is denied in the route map gets filtered in the distribute list. If I'm not using a route map and I'm using an access list, then whatever is denied in the access list gets filtered in the distribute list. If I'm using a prefix list, whatever is denied in the prefix list gets filtered in the distribute list. But you must ensure that you don't forget to put like a permit IP any in the access list or in the prefix list or maybe in the route map also, because even the route map has an implicit deny. So maybe I can do a route. Let's try with the route map. So route map from R1, deny sequence number, let's say 10. And here I would say match IP address, my access list 1. You remember we made one access list which was for offset list. I used the same access list for distance. I'm using the same access list for my route map also. So access list says permit. So if the access list is 151.99, it hits the route map. Route map says deny, which means it should get filtered. And let's create one more route map for everything else. We don't want remaining traffic to get filtered. So we should have another route map with a permit statement, like a permit IP any. Let's just give permit 10,000, sequence number 10,000. And then I can go back to router EIGRP 100, say distribute list, route map from R1 inbound on gig 1.146. So basically, when I receive the route from router 1 on that interface, I would filter that route. which means R6 has no choice but to go through R1, R7 in fact. So let's see, show IP route EIGRP. If I see I don't have 151.99 anymore. Earlier I was receiving 151.99 and now I am filtering that route. So I only have one choice, which is the summary prefix that we had done earlier on R7. He has only one choice. So if I do a trace route now to 151.99, he would go through R7. So you see I can use distribute list also to do a path manipulation. But the only problem is that I don't have a backup with distribute list. I mean, technically, I could go to router 1 and maybe go to my interface gig 1.146, which is towards R6, and say IP summary address EIGRP 100 0000000. I could do something like that. In that case, he would send him a default route. So R6 would have a backup in case if the link to R7 fails. So I could do something like that. Or maybe I make it /23. I summarize again on R1 towards R6. So R7 is sending a summary prefix to R6 as /24, and R1 also summarizes as /23. So just a different way of doing it. It all depends on what you need to do, how you want to do it. We could use an offset list to change metrics to do path selection. We could use distance to do path selection. You could use summarization to do path selection. You could use distribute list to do path selection. Again, all boils down to how they word the question. So let's go back to router 6. And let me in fact go to, I'll remove this. And I will go back to 6. I'm just going to do a quick reboot to my router. So it goes back to my base initials, which we had earlier, where there was no offset list, no route maps, no distribute list, no summarization. I'm just removing all of that. Reload. And in the meanwhile, we would look at load balancing, how EIGRP does load balancing. Now, as you know, in EIGRP, the convergence is pretty fast. We have something called as feasible successor. That's why the convergence of EIGRP is really, really fast, because it has the concept of feasible successor. So we'll look at that, how it does path selection. So let's say I have a router 1 here, and maybe I have one router here, 2. I have another path, 3, and maybe one more, 4. And let's say I have 5, and maybe I have a loop back here. Let's say 5.5.5.5.5. And let's assume that the metric on this link is 10, the metric on this link is 10, and on this link is 10. The metric on this link is 20, and this is 10. And the metric on this link here is 10, and this is 20. Now, if you look at from R1's perspective, R1, if I do a show IP EIGRP neighbors, I would see 3 neighbors. So R1 has 3 neighbors. All the 3 neighbors is giving R1 the route 5.5.5.5, correct? And now R1 has to choose the best path. To choose the best path, he will compare the metrics, total metric. Obviously, to calculate the metric, it's going to be based on the formula, bandwidth plus delay times the constant, depending on whether it's classic or named. But let's look at just this diagram. Assumingly, the metrics are 10, 10, and 10, and 20, 10, 10, and 10, 20, 10. So for R1, if he takes, when he compares the metric for best path selection, when he compares the metric, he compares the total metric from him to destination. So R1 looks at the metric saying, okay, if I take the path through R2, my total metric is 30. If I take the path through R3, my total metric is 40. If I take the path through R4, my total metric is also 40. Are they the same? No. Which is the lowest? Through R2. The lowest is through R2. So that goes in the routing table. So because this, let me change my color. Let's say this. It's because this total distance from here to here is the lowest, which is 30. This path goes in the routing table. So this path would be in the routing table. And this path would be called as successor path, the best path. And the total distance from you to destination is called as FD, feasible distance. So FD is equal to 30. So whenever I compare best path, I always compare FD. What is FD? Total distance from you to destination. That is FD, feasible distance. So total distance from you to destination is FD. He compares the FD of all three paths. So what's the FD of the top path? 30. What's the FD of the middle path? 40. What's the FD of the bottom path? Again, 40. Lowest is top path. That becomes successor path. This path would be in the routing table and topology table as successor path. Now, why is the convergence of EIGRP really good? Because it has the concept of feasible successor, like a backup successor. So what happens to the backup paths? Now I have two more backup paths through R3 or through R4. So now these two paths cannot go in the routing table. They cannot, because they are not equal to 30. The FD is not equal to 30, so they cannot go in the routing table. So they have two choices. Either R1 would discard both the routes, or he would put them in the topology table as a feasible successor. To qualify as a feasible successor, the criteria is advertised distance should be less than feasible distance of successor. Okay? Advertised, this is not administrative distance. This is advertised distance. No, in fact, let's change this to not keep it as AD. Let's name this as reported distance. So what is R3 reporting to R1? R3 is reporting to R1 that my distance to destination is 10 plus 10, 20. Is 20 less than FD of successor? FD of successor was 30. So is 20 less than 30? Yes. So this path qualifies as a feasible successor and will go in topology table. It would not be discarded. The third path, what is R4 reporting to R1? What is his distance? 20 plus 10, 30. Is 30 less than FD of successor? No, it is equal to that. It has to be less. It's equal, so no. So this path gets discarded. This path would not be seen in the topology table. It would not be in the routing table. It would not be in the topology table. It's just discarded. So if the primary path fails R1 because he has a feasible successor, he would not send any queries out to his neighbors for 5555. When I say no queries, it doesn't mean he doesn't send any query. He will send queries, but not for 5555. Because for 5555, he has a feasible successor. So he would not send any queries out to R3 or R4. He would not send any queries. But let's say if this was also 20, in that case, this would also not be a feasible successor. So both the paths would be basically discarded. In that case, if my primary path fails, in that case, R1 would send a query out to both the neighbors asking, do you have the route to 5555? And then they have to acknowledge and send a reply back. They would send the query ahead, and then the reply comes back, and then they would finally converge. But if I do have a feasible successor, in that case, he would not send any queries, and he would directly converge. So if this was 10, then this guy would be, let's in fact go back. So if this was 10, then as soon as this link fails, the feasible successor who was in the topology table will also go in the routing table. No queries out sent. You would not send any queries to any neighbors. I would directly put that route or that path in the routing table as the best path. Obviously, if the primary path comes back up, then again, this would go back into feasible successor, and this path would go back as successor. That's why EIGRP convergence is really fast. Now, EIGRP is the only protocol which actually achieves, which can do unequal cost path load balancing. EIGRP can do that. Let's in fact see that example, how we can achieve that. So let's look at from perspective of our diagram. So what I'm going to do is draw our diagram. So we have R6 here. We have R7 here. And we have R9 here. And R6 connects to R1. R1 connects to R3. And this connects here. And here is where I have 150.1.9.9. Now, as of right now, I've removed all my offset list. I've removed distance. Everything is back to default. So if I look at R6, show access list, I believe it's all gone. Show run, section router, EIGRP. It's all back to default, how it was. So I obviously have two paths, show IP route, EIGRP. Best path is through R7 by default to reach 151.99 because of shorter metric. So if I look at this diagram based on our topology, what's my delay? I'm only using delay for metrics, right? So my delay on this link is 1. My delay on this link is 1. Delay on this link is 1. This is 1. This is 1. And this loop back is 500. So R6 has two paths, through R7 and through R1. So the first thing he would do is find a successor, which is the best path. So he will compare the FD. What's the FD on the top path? 502. What's the FD on the bottom path? That's 1, 2, 3, 4, 504. So bottom path has an FD of 504. Top path has an FD of 502. Top path wins, and that goes in the routing table. Does the backup path qualify as a feasible successor? What is the reported distance by the neighbor to R6? Who's R6's neighbor? R1. What is R1 reporting to R6? What is his FD? 1 plus 1 plus 1 plus 500. 503. Is 503 less than the FD of the top path? No, top path was 502. So this was, let's change the color to orange. So this total all the way to down here, this total was 502, and this total was 504, and the reported distance, which is from here to here, was 503. It's kind of bad color. You hardly can see it. Hopefully you guys can see it. But yeah, it's 503. And I'll just write it down here, 503. All right, so this was the reported distance. Is that less than 502? No. So the backup path gets discarded. Let's verify that first. Let's go back to our router on R6. If I look at show IP route 150.199, in my routing table, I only have one path through R7. If I look at my EIGRP table, show IP or topology table, show IP EIGRP topology 150.199, 255, 255, 255, 255, enter. I only see one path, which is through R7, one successor. I don't see through R1 because through R1 was discarded. It didn't meet the criteria of being a feasible successor. So how can I make R1 into a feasible successor? For you to achieve unequal cost path load balancing, I have to do variance. Default variance is 1. But variance on its own doesn't do anything. Even if I go right now and change my variance to 100, highest is 128, but if I change my variance to, let's say, 100, it's not going to make any difference. Why? Because variance is irrelevant if I don't have a feasible successor. The whole job of variance is to promote a feasible successor into a successor. But if I don't have a feasible successor, who will he promote? So variance has no effect. Let me in fact show you that. I will go back and go to router EIGRP 100, give variance maybe 100. Default is 1. Even if I give variance 100, it doesn't make any difference. Look at my routing table. Show IP route 150.199. I only have one path. And look at my topology table. I still have only one path. So the best path or the successor path would be in the topology table and the routing table. The backup path either gets discarded or gets qualified as a feasible successor. Right now, my backup path has not qualified as a feasible successor, so I won't see it. So variance is only for unequal cost path load balancing, but it does not do anything if you don't have a feasible successor. So for variance to work, you basically need the backup path to qualify as a feasible successor. How can we do that? Let's go back to this drawing board. So how do I make the backup path qualify? Again, this is pure maths, right? So this is 503. I need this to be higher than 503. So maybe I go to R6 and change this to 2. If I make this 2, it becomes 503. But would that qualify? What is the requirement? Reported distance must be less. It cannot be equal. It has to be less. So if I change this to 3, in that case, this becomes 504. But the problem would be, this is 504. This FD is also 504. Reported distance is 503, but total FD is 504, which means now both the FDs are same. Load balancing would happen, not because of variance, because of equal cost path load balancing. Do I want that? No, because think about it. Let's say if you had a 10 gig link and you had a fast Ethernet. Why would you want to do a 1:1 ratio load balancing? You don't want that. Because there would be congestion on fast Ethernet maybe, and maybe it's faster on the gig port or 10 gig port. So this would be a problem. So maybe I go to R6, change this to 3, and change this to 2. What's going to happen now? What's my FD on the top path? 504 after I make the change. What's my FD on the bottom path? 505. They're not the same. So top path goes in the routing table and would be in the topology table as successor. Now, does the backup path qualify as a feasible successor? 503 is less than 504. Yes. So that path would go in the topology table as a feasible successor. Let's test that. Let's go back to my router and go to my interface, gig 1.67, and say delay. Let's change this to 3. And 146, let's change this to delay 2. Default was 1. Once I did this, look at my routing table now. Show IP route 151.99. So temporarily I have both the routes in the routing table, but because I gave variance, the second path also came in the routing table. Let me in fact go and remove that from the routing table now. Let me go and remove the variance temporarily. Router EIGRP 100 and set the variance back to 1, which is default. Let's look at the routing table. I only have one path, top path, which is, if you see my delay is 504, which was as per that diagram that we saw, 504 was my delay. And if I look at my topology table, this time I should see the backup path in my topology table as a feasible successor, which I do see R1. I have one successor, which is through R7. Always the successor would be on top. So one successor, and then I have the backup path, which has qualified as a feasible successor. So is he going to load balance right now? No, because the variance is 1. He's not going to load balance. Only the best path would go in the routing table. The backup path is now a feasible successor, waiting for the primary path to fail. If that path fails, no queries would be sent, and this path goes directly in the routing table as successor. But let's say if I do want to achieve load balancing, unequal cost path load balancing, if I do want to achieve that, I could go and change my variance. So now if I go and give variance, let's say variance 100, doesn't matter. What's the criteria for the load balancing? What's the criteria for variance to work? What's the job of variance? To promote feasible successor into a successor. That's the job of variance. So when will that work? What's the criteria? The criteria is feasible distance of backup path should be less than or equal to is okay here. So for feasible successor, it had to be less than the FD. But for unequal cost path load balancing, it always compares not reported distance, but the feasible distance, total distance. So feasible distance of backup should be less than or equal to feasible distance of primary times variance. So what is this FD of the backup? 505. Is it less than or equal to 504 times my variance was 100? Yes. So backup path qualifies to get promoted as a successor. So looking back now at my routing table, show IP route, I would now see two paths in my routing table. Both the paths are there. And in my topology table, I would now see two paths, both as successor, two successors. So both have become successors. The only problem is that if I look at the share count, it is 1:1, which is not really good. It's not good. It's not something that you would desire. Because imagine, like I said, imagine having a 10 gig link and a 1 gig link. So something to think of when you have slower links versus you have a faster link. Why would you want to do a 1:1 share? You want to use both your links. So the company says that we're paying for the backup link. Let's use both the links. Maybe traffic, like undesired traffic, like BitTorrent, or maybe something which is not desired, FTP or something, can go from the bottom link. But important traffic can go from the top link. But you never want to do a 1:1 ratio because there would always be congestion then at the bottom link. So assumingly the top link was 10 gig and the bottom link was 1 gig, assumingly. In that case, my share count should be 10:1, 10 packets going to the primary link and 1 going to the backup. So you can change your share count also to do unequal cost path load balancing or path selection based on the share count. So let's try to do that. Let's try and achieve 1:10. So 1 packet goes to the backup and maybe 10 packets goes to the primary. So to achieve this, let's go back to the drawing board. So we have to think about all the things to achieve that. So what is the best path FD? 504. When will my ratio be 1:10? If the backup path is 10 times slower, right? Which means the metric has to be 10 times higher. Which means, what is 10 times of 504? Which means this is the primary, and 10 times of primary would be 5040. This should be the FD of backup. So this is the FD of primary, which is right now 504. This should be the FD of the backup, but still keeping in mind that it still qualifies as a feasible successor. It must qualify as a feasible successor, otherwise variance won't do anything. So what I will do, I will keep my 503, which is the reported distance, same. I won't change that. What I will do is I will calculate this value. I will calculate this. So what do I need? I need the total to be 5040, right? Because I want 10:1 ratio. And what is this? What is the reported distance? 503. So let's subtract 5040 minus 503 equals, I think it's 4537. I think it's 4537. But we'll still use a calculator just to be sure. 5040 minus 503, 4537. So I will go to this interface and put the delay as 4537. If I put the delay as 4537, now think about it. Which is the best path? Top path, 504. What is the lower path, FD? 5040. So they both are not the same. So top path goes in the routing table. Does the backup path qualify? Yes, 503 is less than 504. So it becomes feasible successor. Now I have a variance. What does variance do? What is the FD of backup? 5040. Is it less than or equal to 504 times the variance? So 504 times 100 is 50400. So obviously it does qualify. So it should give me it should do unequal cost path load balancing, at the same time do 1:10 ratio. Let's try and configure this. I will go to my interface gig 1. What is it, 146. Oh, it's 146. And say delay 4537. The minute I do this, let's look at my topology table first. Is it still there in my topology table? They both should be successors. So I have both of them as successors because of variance. Obviously, they're not equal cost path. They're unequal. So because of variance, I have two successors. And if I do a show IP route 151.99, I see a 1:10 share count where 10 packet goes to the primary segment or primary link or primary ISP or whatever you want to call it, but the primary side, and 1 goes to the backup. So you see, path selection is pretty straightforward. It all depends on how you want to use it. You should know different features which are available in EIGRP to do route manipulation, path selection. EIGRP does equal cost path automatically, unequal cost path through variance, but you must qualify as a feasible successor. And you can do distribute list to filter routes, you can do offset list, you can do distance, you can do summarization. So many ways of actually achieving this. So I hope you guys enjoyed the webinar. I will answer some of your questions now. Let me go to question and answers. All right. So I see one question which says, will you do a webinar on Ospf? So I don't really have anything scheduled for Ospf, but if there is a requirement for that, yes, I could do something for Ospf. And the next question is this a virtual environment? And is it based on INE CCIE Workbook topology? It is a virtual environment, and it is based on INE's Workbook topology, so you can load initial configs from the control panel. Then I see a question in secure CRT, how do you get IPs to show in red? For that, you only have to download a script which is available on Google. Just search for a script for secure CRT. I see another question. How is delay calculated? So delay is, if it's classic, it is total delay divided by 10. That's your delay. What you see in the show command does not show you in tens of it shows you in microseconds. But when you actually enter the command on the interface, it's in tens of microseconds. So that's why we divide by 10. So the actual delay is 504. It's not 5040. So because the show command shows you microsecond versus it's in tens of microseconds. So, I mean, that's how it is. I mean, Cisco has always been consistent in being inconsistent. So that's how it is. And then I see a question, 64-bit metric is called as wide metrics. So yes, it does support wide metrics. And in IPv6 routing table 128-bit, correct. And I don't understand the question actually. So I see another question which says, does EIGRP convert the metric to 128 bits in case of IPv6? So if you're running named EIGRP, it would convert everything to the required format as per the routing table. So EIGRP is named EIGRP is 64-bit and routing table is always 32-bit. See, when I say 128 bits, that's the addressing format versus the routing table, how many blocks they've reserved for the routing table, for the metrics. So it's two different things. I see another question. Can you explain why sometimes COMPTED distance is different than feasible distance. So that really depends on whether you've applied some offset list or not. So if you do apply some offset list, then your distance in the topology table would show different from what you actually see in the routing table. So it's not always the same that you use a formula as per what I showed you. It all depends on what you've configured, whether you're using name or you're using EIGRP Classic. So it all depends on that. And then I see another question. Is this command IP summary address suppress the prefix? So the IP summary address was for summarization. So if you remember, I did on R1 IP summary address 0000. So in that case, he never sent any prefixes to R6. He just sent him one default route. And then I see a question. If the default uses bandwidth and delay, how do you make it to use only delay? You have to change the K values. So if you do a show IP protocols, you would see that the default K value is bandwidth K1 is 1, K3 is 1, and K2, K4, and K5 is 0, which means K1 is bandwidth, K3 is delay. So only bandwidth and delay would be used. If you go and change your metric weights, so what I've done, what I actually pre-configured in my initials, I went ahead and gave the metric weights, where I said this was for bandwidth, and so this is K1, K2, K3. I only kept K3 turned on. Everything else was turned off. And this 0, the first one, is toss field, which is always 0. So that the K values start from here. Okay. I see another question. If both paths have an FD of 40, what's the tiebreaker? They both would become successor. They both would go in the routing table because the FD is same. So they both, because EIGRP has a maximum path of 4 by default, so it would load balance. Then I see another question is, when you increase the delay to 4537, why it is selected as feasible successor? Because I only increased the delay on this link. That changing the delay only affects FD, does not affect reported distance. The reported distance is still 503. That's why it qualifies as a feasible successor. So when I changed when I gave 4537, it only changed my total FD. It never changed my reported distance. That's why it qualifies as a feasible successor. And then I see a question, is there unequal cost path load balancing in Ospf? No, Ospf does equal cost path. And then there's a question of MPLS. So, so please repeat the difference between RD and FD, so reported distance and FD. So FD is the total distance from you to destination. Reported distance is the total metric from your neighbor to destination. So what is your neighbor reporting to you? So neighbor's FD for you would be RD. So FD is from your perspective, let's say from R6's perspective, FD is from R6 to R9's loopback. And AD for R6 or reported distance for R6 would be from 1 to R9. That's the reported distance. Okay. And I see another question is, can you show how you change the prefix list length for the route for R1 and R6? I did summarization. So I reduced the route, the prefix length. So because R9 was advertising /32, I did summarization to make it /24. So that longer match would be preferred. And I see a request for BGP traffic engineering. I can have a look at that. In fact, I was thinking of doing BGP in the next webinar. So let's see. Can we change the RIP scale? Yes, default is 128. You can adjust that lower or higher. Highest is 255. And I see another question, which is the reason I multiplied by 10 because we want a traffic packet flow 1:10. Yes. If I want 1:5, I would multiply the FD of the primary path by 5. And that should be the FD of your backup. And then I see another question, which is a pretty interesting one, which says, instead of setting offset lists, we could set the metric in the route map by matching a tag versus using offset list. Yes, you could. You could probably create an access list, match a specific prefix, or if there's a tag already present, you could match the tag and set the metric for that specific route. And maybe apply that to the neighbor. So yes, you could do that. But it's like doing it the hard way if there's an easier solution available. But yes, you could do that. And then I see a question. Does EIGRP does load balancing automatically? Yes. So if it's equal cost, all routing protocols will do load balancing. I mean, except BGP. But BGP can also do, but you need a command for that. But Ospf will do load balancing. RIP would do, EIGRP would do, if it's equal cost. And then there is one question which says, can you explain who EIGRP would prevent any loop due to explain formula of feasible successor? I don't really understand that question. Can you explain who EIGRP would prevent any loop due to explain formula of feasible successor? No, I don't really know. I don't understand the question actually. But if you want, you can email me and I can answer. Okay, so I hope you guys enjoyed the webinar. If you do have any questions, feel free to email me. You can email me on my email address. Let me in fact write it down for you. You can email me on rohit@ine.com. So email me here, or you could even send me a request on LinkedIn and I can answer the question. I hope you guys are safe and thank you for taking your time for this webinar.